So now our next speaker is Malte Meinshausen, and he'll be online talking about MAGICC mitigation pathways and carbon budgets. He has a sort of background, PhD from Zurich. He then had a long period as a senior researcher at the Potsdam Institute for Climate Impact Research, and then he moved to Australia, where he founded the Climate and Energy College at the University of Melbourne, where he's speaking from today. His main research activity really relates to carbon budgets, climate scenarios, and the reduced complexity model MAGICC, which Tim mentioned in his opening remarks. And he's made a lot of important contributions to the IPCC and to international climate policy. So this is a 25-minute session. So if you can keep, Malte, if you're there, if you can keep your talk to maybe like 20, 22 minutes and allow some discussion, that would be great. Thank you very much.
Thank you so much. Thank you so much for having me. And yeah, please interrupt me if I'm too long, but it could well be that I don't have so much to say. Anyway, first of all, I have a confession to make. In 1999-2000, I wanted to learn English. I got an offer for the MSc of, I think, climate change at the UAE. And then in the end, I did not take that offer. I would have been a much better climate scientist if I had taken it, but I ended up at Club Mediterranee with Miles Allen as one of the lecturers when I took up the MSc in Environmental Change and Management in Oxford. So these are one of the regrets in life. And but I was incredibly fortunate to meet on my pathway Tom Wigley and Sarah Raper, and I hope Sarah Raper is with you in the auditorium. And yeah, the very fond memories, for example, of sitting in a little sailing boat dinghy in Potsdam with Tom Wigley, Sarah Raper, and myself, strong winds, and two gentlemen had very pale faces, and a very chirpy Sarah Raper steering the boat through the waves. And yeah, it was very good. And we had a long-standing collaboration. So all the work around MAGICC really unfolded thanks to them. They are the parents, or by now almost the grandparents of MAGICC, because I'm about to pass MAGICC on to the next generation of postdocs. Yeah, and so this is this talk is meant to be a little homage to MAGICC and where it is now used everywhere, really originating at CRU and celebrating one of the many things that CRU gave to climate science around the world. Okay, so here are the not so humble beginnings of MAGICC. 1985, a Nature paper by Tom Wigley and Michael Schlesinger, another Nature paper, Wigley, Sarah and Tom, and yet another Nature paper on the IPCC emission scenarios. And I think just for a change, this was a science paper in 2001 by Tom and Sarah, always using MAGICC. And here also by Tom in 2006, a science paper. So there were pretty big shoes to fill. And then Malte came along writing up all the code of MAGICC in atmospheric chemistry and physics. But luckily, MAGICC has such a shine that in the end, we made it together with Miles Allen's studies on the Nature cover in 2009. And that was about basically the carbon budget and how much emissions, how much of our fossil fuel reserves we can burn in order to stay below a certain temperature level with a certain likelihood. And I'm not sure whether it was really the first. There were similar thoughts beforehand, but I think it now was often at least described as one of the birth hours of the carbon budget, which was then taken up in many IPCC reports and is still some of the milestone guardrails for international climate policy and how to be fair. Underlying that was our approach to do a really big sampling of all the simple climate model parameters. Simple climate model, MAGICC has around 400 input parameters, and 80 or so we sampled. It's only 10 of them that, of course, have a substantial impact on, for example, global mean temperatures or ocean heat uptake. But it's important to sample quite a few more just because they create the noise and that can change the joint distribution among the other parameters. So this is what we did 2009. But in the course of the sixth assessment report, we did something very similar again. Monte Carlo Markov chain here done spearheaded by my colleague Zebedee Nichols. And what we did is not only compare to global mean historical observations of surface air temperature, but also ocean heat uptake and a few other key assessment line items of the IPCC, the different aerosol forcings, the greenhouse gas forcings, ECS, TCR, et cetera. And so we tried to really use the simple models now, not as models in their own rights, but as emulators. And that's why also you find the term emulators a lot in the latest IPCC report, because it's really meant to emulate the whole wisdom that comes together from the CMAP6 ESMs, but also from the other lines of evidence that inform our knowledge about equilibrium climate sensitivity, or TCR. And so there was a rather, I think for IPCC was one of the first times that it was a rather elaborate process, all the calibration and tuning. We had 4 simple climate models there in the run. And here in the cross chapter box in 7.1, you will see here's also MAGICC in the 3rd column. And yeah, it didn't do too badly. The colored areas are where there's some deviations from either the assessed ranges. Not all deviations have to mean that the simple climate model is not perfectly calibrated, etc. It can also unveil some inconsistencies in the assessment. If one chapter makes an assessment of climate sensitivities in a certain range, of course, in IPCC terms is always rounded a little bit, but then TCR is maybe there, and maybe both of them together with the aerosol uncertainty don't really go together if we believe the structural way that these simple models, of course, reflect the climate. Anyway, MAGICC did pretty good. And also for the lowest scenarios, there's a slight too strong cooling, or maybe the IPCC assessed range is slightly too warm for fair. It's even a bit stronger cooling in the lowest ranges, but otherwise, here MAGICC is pretty spot on for the central assessed temperature ranges across these different scenarios. That can be then used to, for example, in working group 3, where we have 1,200 scenarios in the end vetted in that database. And Tim mentioned it in the beginning. If we wanted to run ESMs for every one of them, then that would be quite a bit. So if we run these 1,200 scenarios with 600 ensemble members each, we have immediately something of 720,000 MAGICC runs that we have to do in every iteration. And you can imagine in an IPCC process, after a few days, you discover, we have to run it again. So luckily, we have now cloud computing and scalable services. And so some clever software engineers, Jared Lewis in this case, scaled the whole thing, and now it can be run within a few hours, which previously would have taken a few weeks, even with MAGICC, even with such a simple model on a good server. Anyway, we have here all the different scenario classes, for example, from working group 3, and they were all assessed with MAGICC, but also with the ranges also informed by FAIR. And that is quite important material for policymakers, because in the end, they want to know which scenario gets them to 1.5 or below 2 degrees, with what likelihood, and what are my options on these scenarios. It wasn't only used for global mean temperature change. There's also something where you, for example, inform the carbon budget, and you use these climate emulators in their probabilistic setup for determining the non-CO2 warming, because that is an important component in order to find out what the remaining carbon budget is. And here you see that table where in the latest Working Group 1 report of IPCC, MAGICC, and the other climate emulators were used in which of the chapters. Also, before the whole circus starts, so to inform as input to the CMAP6 exercises, MAGICC has been used for CMAP5 and CMAP6 to project the greenhouse gas concentrations. As we still have our normal experiments in CMAP still concentration driven, even though most models could now run emission driven for CO2, but for the other greenhouse gases, that is not the case yet. I think there are only 2 or a few that can do it for methane, run with emissions rather than concentrations, but also for the other little gases, it probably doesn't even make computational sense if they carry around all these gases. So therefore, MAGICC is used, and there we did these new concentration input fields with seasonality, with latitudinal resolution, etc., which maybe not many models have used, but hopefully in the future. And now I will come to a few more slides generally about, because Tim asked me to also talk about mitigation pathways and carbon budgets. So one of the key headline statements from IPCC was, unless there are needed rapid large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees will be beyond reach. These are, of course, the grand statements that we all know. However, there was quite a bit of discussion this time in IPCC about is, for example, one headline statement that 1.5 degrees crossed 10 years earlier, or do we say it's lost, etc. So, and for that, funnily enough, these 0.1 degree calibration errors actually start to matter, because for policymakers, if they hear, well, the lowest scenario goes to 1.55, that has a big influence. Anyway, that framing is important. Here I show you a graph of the latest UNFCCC synthesis report last year. And as some of you might know, this week there's also the new UNEP gap report coming out, quantifying the emission gap, so the difference between where all the targets of the countries take us in 2030 and where we would want to be in with 1.5 and 2 degree ambition. And the UNFCCC synthesis report is also coming out this week. Anyway, here are the historical emissions. These are the indices where they take us to 2030, and you can imagine what that picture looks like. If we plot here the 2 degree or 1.5, or even strictly below 1.5 degree scenarios, then there's quite a big gap here in 2030. Now the indices came down a little bit, so this week you will probably see updates that this is here now 5 gigatons or something lower than it was originally during the time of Paris, but still the overall picture is pretty much unchanged. You have rather flatlining emissions up to 2030, and if we wanted to be on the cost optimal trajectories for 2 degrees or 1.5 degrees, we would have to be quite somewhere else. One could still achieve 2 degrees if one goes to 2030 emission levels and then goes steeper down, but that comes with additional cost and it requires reduction rates that we could avoid if we started more mitigation action this decade. Lucky enough, we can slightly keep up. No, we can't keep up with the production of Nature and Science papers of Sarah and Tom in the early days, but every 10 years we get a Nature cover. And so this was one here, quantifying all these climate pledges and then coming to the conclusion that with the long-term net zero targets, we are just around the 2 degree mark. Not well below 2 degree, but we are just around the 2 degree mark if these pledges are actually implemented. And for that, of course, it depends on climate policies being implemented. It also depends on climate finance, the support being given to developing countries that ask for those in order to fulfill their conditional NDC pledges. Now, if we look at just the median projections or the orange areas, so the unconditional pledges, blue areas, the conditional ones, then around the time of the Paris Agreement, we were at around 3 degrees. And then the countries put the different pledges on the table. And then towards Glasgow COP26, we had quite a few coming to the table. And in the end, China and the announcement by India that was formalized this year as an NDC, that really brought us towards the 2-degree mark. However, the net zero targets in 2050, they're good, but the 2030 targets of the NDCs, they are not on the trajectory. They're not getting us there. So therefore, it's really about bringing the 2030 emissions down in order to be on the trajectory to have a chance to then achieve the net zero targets later on. It's also important when you look at it from a carbon budget perspective, which we come to here. So if that is a carbon budget for 2 degrees, and this is how much we ate up in the past, and this is how much the NDCs will eat, and this is then the remaining part of the pie. But you all know what the picture is looking for, 1.5 degrees. This is what we ate in the past, and with the NDCs up to 2030, as they are on the table right now, we pretty much eat up the 1.5 degree budget. Okay, and then just to support a little bit the discussion, a few more climate science policy challenges. For example, GWP star, I think it's a topic only here in New Zealand and Australia. I hope it's not in the UK. But anyway, that is one in the climate policy field. The net zero, the transition from the avoidance offsets, it's really a time to call offsets to an end that are just avoidance offsets, but looking at then durable removal offsets. So if you put an emission into the atmosphere, really you have to take one out of the atmosphere again if you want to offset. Move from net zero to net negative targets, make the attribution and liability across the whole cause effect chain watertight that allows loss and damage attribution. And then the regional probabilistic results, we saw many CRU initiatives going in that direction, and that is fantastic. And we are still so far away from really putting good probabilistic information out there, and we can see it in all the TCFD discussions that the climate science information is often lacking to compare to what the industry wants in terms of robust probabilistic regional or local information. I skip over that. I think I just mentioned that here. Since I criticized Miles Allen's GWP star, I also give him credit for this, that we need to go to a durable net zero, which is not taking more fossil fuel carbon out of the lithosphere than putting back in. And because otherwise we can't just offset our way with planting little trees. And then this is about the regional stuff. And if you want to look at where MAGICC sits at the moment, it's at livemagic.org. They have an user interface. You also have the CRU logo there, and you can nicely play around. You can upload your own scenario, and you can see the categorization just as it is done for IPCC. And MAGICC is also going to go open source. There's the ESM 2025 project at the moment where people do it in a very modularized way, very fancy from a software engineering point of view, but hopefully then many contributors can work on it in the future. I say thank you, and most thanks goes to Sarah Raper, who is in the room, and Tom Wrigley, who is hopefully online, I don't know. But yeah, I stop here and thank you for that.
Thank you very much. And so there's actually plenty of time for questions and discussion. So So the floor is open for comments as well, I suppose. That doesn't have to be questions. There's lots of experience in the room, maybe comment, thoughts. Tim. I'll give you.
Mike here, it's okay.
Okay.
Hi Malte, thank you for your talk. I wonder if you had any brief comments on what I said in my opening about others in the IPCC's views of simple or reduced complexity models evolving over time between waiting to get rid of them to now being impossible to get rid of. Does that match your experience?
Yes, and I would hope. Oh, now I'm gone from the screen. There. I hope that Thomas Stocker is not in your room, but Thomas Stocker, head of AR5, told me quite clearly that the time of simple climate models is over and not anymore. We have ESMs and we have EMICs and that's it. And then simple climate models came back also in the AR5 because, as you said, I think it's realized that it's hard to do without, and they have their niche. And of course, they don't produce the same knowledge as ESMs and EMICs, and you can't, but they have their niche in combining a lot of knowledge, combining a lot of domain specialized knowledge in that highly aggregated way. If we want to find out for lots of scenarios, what are global mean temperatures with which we can then drive a lot of other domain models, like whether it's regional extremes, whether it's Arctic sea ice, etc. We then can use the incredible power that these simple models they have. But again, they're not on their own right. They need to be calibrated to the ESMs, and then they need to be calibrated to observations, etc. And once they manage that successfully, they are quite useful tools. Even more so now used in AR6 in order to translate the ECS and TCR knowledge into the future temperature projections, and there are different simple models around. And I think over time, probably thanks also to the early success of people like Sarah and Tom, there was also the legitimate feeling in the ESM community, hey, wait a second, all these Nature and Science papers, they take the limelight from us. Why? No, stop to that. And I think it rejigged into a balance. We should avoid writing too many Nature and Science papers with maybe for the future. Now, I completely agree with what you said in your introduction.
Thank you. Any other comments or questions? Nem. You've got a microphone too.
Yeah, I think that works, right? Thanks for that talk, that was brilliant. I just wanted to ask, I was reflecting on your point about these the kind of conversation when, particularly the role MAGICC plays in helping with that conversation from science into policy, and the headline target's about 1.5. But the challenge is maybe on an AR7 cycle and the kind of role that MAGICC might play in helping there with, things that are 1.55 or 1.56, that comment that you made. And I just wonder what your reflections are in that next AR7 cycle, and how having those conversations about 1.5 and the risk one can see in the next few years of, how the message between hitting a global mean average temperature of 1.5 was reported by CRU this year versus all the work that goes into the kind of messaging that comes out of IPCC.
Well, for the AR7 cycle, it's going to be interesting because probably before AR7 comes out, we are going to have a single year that has global mean average temperatures already around 1.5. We already had individual months around 1.5. So the public will ask themselves, hey, is the target now lost? And then the big communication challenge is, if you exceed a speed limit of 100 kilometers per hour on the highway and you drive 120, is then the speed limit lost? No, it's not. You have to go under the brakes. And that kind of, if we go to net zero greenhouse gas emissions, we can slowly pull global mean temperatures back. And if we reach 1.5 from slightly from above, then maybe that is the best we can do. So I think we have to separate the discussion about is the target lost, because no, 1.5, so even if we would go to 2 degrees, the target could still be 1.5 and could be very valid. So maybe even more important because we see all the impacts that are happening at 2 degrees. But of course, it should be getting that nuance into the public debate that we should do as much as we can, stay as close as possible to 1.5 degree. In fact, the scenarios that were around about 1.5 degrees at the time of the Paris Agreement, they were defining 1.5 degree scenarios in the UNEP report back then by their 2100 temperatures. They had slight overshoots. That is not much different to what we have now. And so big headline statements about now 1.5 degrees is lost, we cross it, and we cross it 10 years earlier, etc. That is kind of slightly unfortunate in my point of view. We have to highlight the dangers of overshooting, absolutely. But at the same time, we can also be incredibly fortunate of having lots of low-cost renewables in the back, where us climate scientists standing there and saying we should do more is probably doing not even 5% of the motor that is now sitting, or the big gorilla that is sitting in our backs, just the renewable energy transition, and that gives us a lot of hope.
Okay, I think we probably better move on. Oh, Rachel, okay, well, one last question. So,
Hi, Malte. So a couple of questions. I've switched it on.
we can hear you.
Okay.
Yeah,
a couple of questions. So the first one is, so the discussion about simple models earlier, and obviously when looking at carbon budgets, feedbacks in the Earth system are very important. And some of these processes may not be that well captured by even global circulation models. So I know that in AR6 there was some work done to incorporate feedbacks in the Earth system in the budget. I wonder if you know anything about that. If not, no worries. The other question I have for you is, why do you think that the 1.5 and 2 degree scenarios are based on only 67% probability? Because we are talking about the future of the whole planet here, and for a single nuclear power station, we require something like 99.999% certainty that it's not going to explode. So why do you think that policymakers went with only 67% chance of protecting the entire Earth?
Good, 2 questions. The first one, yes, Earth system feedbacks are included, and there's a big table in chapter 5 of Working Group 1 that has the class-based feedbacks, Amazon dieback, but most importantly, more the traditional CO2 fertilization, climate feedback on the carbon cycle, permafrost, etc. So that is all, to the best of our knowledge, included. There's no missing feedback, but of course there are unknowns. To the second question, why probabilities of 67% and not 99%? I would say for some other reason, we should probably go more towards the 50% budgets and the 50% targets. We can set the temperature lower, but setting the likelihoods very high has one side effect, is because we get slightly better with our climate knowledge over the years, or we come simply closer to the threshold. If you have a target that tells you should be 99% certain, then at the moment you would stay completely below, you would stop emitting, etc. But every year there will be a more, there could be a higher carbon budget because you get more certainty And then if you get more certainty, if you get closer to 1.5, you would have an expanding carbon budget for the next 10, 15 years, because at the moment you would basically start at 0 and then it would go up. And that doesn't really infuse confidence in climate policy either. And that is similar a little bit with the 67% and with the 83%, that if you really crank up your likelihood, then you have an 83% chance that in the next assessment cycle, you are going to tell policymakers, hey, by the way, now it's 200 gigatons higher. And so that 83% chance of constantly having to revise upwards your milestones is not necessarily a useful message for the larger public, I would say. That does not mean that we should take 1.5 or 2 degrees lightly. We should do everything we can to stay as close as possible to 1.5. But I would say, rather than setting 90% target for 1.5, then have an aim of 1.4 degrees, etc. Anyway, I think I hope I made my point. Of course, also 1.5 and 2 degrees are not thresholds where there's a cliff afterwards, as you know better than I do. It's all the gradual targets. So I think with targets where we have tight temperatures, but it's more geared towards our best estimate, we are better served in the long term giving advice to climate policymakers.
Well, thank you very much indeed. Right.